Okay, good afternoon. Continue on with FET. Today we look at describing some of the equations related to each of the MOSFET regions of operation, right? Okay, modes of operation. All right, so in FET, we need to apply a certain voltage at the gate so that the channel is created, right? Enhancement mode MOSFET. And any voltage that is applied in excess of this threshold voltage is known as the gate overdrive voltage. Here in the notes, we refer to it as delta VGS. Just FYI, in the book, if anyone has read it, what is it called? Anyone? It was VOV, voltage overdrive. So if you're reading the book and you're trying to solve the problems from the book, then delta VGS in the notes is same as VOV that's in the book. As you go along, you may have encountered this in the in your previous classes. If you read the same topic written by 3 or 4 different people, every one of them might have a certain notation or a certain way of referring or describing those things. So this is one of those quantities. Okay. So our author prefers to use VOV. So just wanted to let that know before we proceeded. All right. So we have 3 regions of operation: prior or linear, active or saturation, and cutoff. Then talked about obtaining threshold voltage from the characteristic transconductance GM, which is of course a process parameter, right? Depends on the applied voltage and the applied current. Then we define the conductance parameter K. Okay, and this is not a process parameter, as you can see from the equation. This is a design parameter. Okay, W or L mu COX over 2. All right, so this is basically indicating, the K is basically indicating the ability of the channel to conduct current. Okay, and so it depends on the physical dimensions and the doping profile. Hence, it's a design parameter. Okay, it's a design parameter. So K again is conductance, or if you will transconductance, then it's units or amps per volt square. W is the cross-sectional width of the channel. So if we had a 3-dimensional image, let's say something like this. Right, and you'd have a channel between your drain and source regions. And then W is the width of the channel. Length is L, noted by this. And then COX is the gate channel capacitance. Because you have 2 sort of conducting plates separated by an insulating material, there's a capacitance that is associated with that gate. It is known as the gate oxide capacitance, COX. That, by the way, is incorrect. I don't know why I translated like that. OX is the entire subscript for COX. It's not C subscript O and subscript X. So this should have been a subscript. Anyway, that refers to the capacitance of the gate oxide. And then mu is the carrier mobility. So that is for either electrons or holes. If it's N channel, if it's N-type material, then it's the mobility of electrons. If it's P-type channel, then it's the mobility of holes. And this is something we encountered early on in chapters 1 and 2. Okay, so that's the conductance parameter. Again, as I was saying, this is a design parameter, whereas the transconductance GM is a process parameter, because GM is directly the ratio of the change in drain current as a response to change in the gate source voltage, delta ID over delta VGS. Okay, so we can now describe ID, drain current ID. By the way, you always refer to drain current, right? Because the electrons are moving from the source to the drain, so the current is flowing from drain to source. So we describe it as drain current ID. But again, disregarding the fact that the body might be connected to the source or the drain, this is a symmetrical device. If it's a symmetrical device and the current's flowing just between those two terminals, it is the same as the source current IS. Okay, so the drain current and source current would be the same because they are flowing between those two terminals. Okay, so drain current ID, we can use different equations to describe drain current, but we can boil them down to like 3 major equations for each of those 3 regions. Okay. In the cutoff region, what is the equation for the drain current? Anybody? 0. Obviously, it's cut off. There's no channel. Because there's no channel, no current. All right. Then we have the triode region. In the triode region, the first criteria for the linear relationship is that VGS must be greater than the threshold voltage, VTN. Right? Establishes the channel, and then VGD, sorry, VGS is greater than the threshold voltage, and VGD is also greater than VGS. Let's see, where is this one? Okay. All right, so triode region ID can be given by the conductance parameter K times 2 delta VGS. But since we are referring to the book, I'm going to use the book's notation 2OV minus the drain source voltage VDS times VDS. This, of course, requires that the channel is established. Yes. VGS when GB, the body to gate voltage. How? Let's see. The question being asked is, how is VGS affecting it? Because we need carriers from each of these implanted regions to form the channel. So we have this device, right? And we have this implanted. Whether it's P-type or N-type is immaterial right now. We apply a voltage at the gate. I'm not drawing the oxide. We apply a voltage at the gate is going to pull the minority carriers to the surface. Those minority carriers will form a thin layer, but that's not sufficient to simply form a channel between the two regions. If we don't bias, source and the drain, if we don't bias the source and the drain, there is no there would not be sufficient connect. There will be a channel. Yeah, if you ignore VGS, there might be a channel, but it's not going to be sufficient to enable current flow because it's only comprised of minority carriers. But when you bias the source and the drain, you have carriers coming in from here because these are either N plus, so the drain and source are N plus or P plus, meaning they're heavily doped compared to the body, compared to the bulk. So the most straightforward answer is if you do not bias the gate, and I mean, if you do not bias the drain and the source, meaning VGS, and if we just do VGB, then it's only going to pull carriers from the body or the bulk of the substrate. In order to have a channel big enough with enough free carriers to conduct between the drain and the source, we need to bias the drain and the source so that the carriers also come from the drain and the source. In which one? It is there. It is there. We're just not looking at everything. We need an entire academic, well, I wouldn't say an entire academic year, but at least one entire quarter to delve into all the equations, which you can do if you want to take the 306 and 307, which CPA students will take in the semesters. But let's get back on track. I'd love to keep discussing that. I think it shows you have an interest in doing things. But again, also keep in mind the body is shorted with the source be the bulk. No, because we need to keep it reverse bias. So for most of the devices, especially the ones that you buy off the shelf, the body will be shorted with the source. Also with the integrated MOSFETs we looked at in the chip, the source was shorted to the body. So you are applying voltage to both of them. You're reverse biasing both of them. Okay. So this was the triode region. Let's look at the active or saturation region. So in the saturation region, VGS is of course greater than VTN or the threshold voltage. But VGD is less than the threshold voltage, meaning VDS would be greater than VOV, which is of course greater than 0. And ID be approximately equal to K times VOV square. It reaches a saturation level because the channel is now almost pinched off. There are a couple of other approximations. I'm not going to go through everything, but it's part of the assigned reading. So in the book, when you read through it, there are a couple of other equations based on certain voltage conditions. So please be sure to read those. These are the two main ones. Okay. So let's look at an example. What? Untitled page. So there. All right, let's look at some examples where we can determine the operating state of a MOSFET based off our measurements, right? So here you have a MOSFET biased with VGG and VDD. Simply apply DC voltages on the input and the output side. And you're measuring the current, the drain current, and you're measuring the drain source voltage, VDS and ID. All right, so the question being asked is, determine the operating mode or determine the operating state of this device. Worst case, VGG value is given as 1 volt. VDD value is given as 10 volts. Measured VDS is fully 10 volts. ID is 0 milliamps. And RD value is 100 ohms. So, wild guesses on the first one. We don't even need to do any analysis or calculations. Question? You said you mentioned something? Yeah, it's cut off. Drain current 0. So it's cut off. It's an off switch. As easy as that. It's like the BJT mode of operation. If the base emitter junction is not 0.7 volts, then that junction is off, meaning the transistor, the BJT is completely off. That's the first step to see. So in the MOSFET, so VBE, we check the drain current. If the drain current is 0, then it's completely off. Good. Okay. As I said, we didn't need to do any calculations for the first one. All right. So the next case, VGG is equal to 4 volts. VDD is 10 volts. VDS measured is 2.8, which of course means that there should be some drain current. In this case, it's given as 72 milliamps. And RD is still 100 ohms. So we have our supply voltages, we have the measured VDS and measured ID. And in this case, ID is not 0. So what are the first steps we can take? Well, we can look at, first of all, the levels of the voltages. In this case, since VGS, we can determine VGS from these values. Okay. So VGG is 4 volts, and we are applying 4 volts to the gate, right? And unlike a BJT, current does not actually flow into an FET because of the oxide layer. We're simply applying a difference, applying an electric field or an external voltage. So VGS is equal to VGG is equal to 4 volts. Oh, just don't want to miss 2 of the important things right here. Threshold voltage is given as 2 volts and K is given as 18 milliamp per volt square. So first step, applied VGG. Applied VGG is 4 volts. So VGS is 4 volts. So is the MOSFET in overdrive? Has channel been formed? Anyone? Threshold voltage is 2 volts. Applied voltage is 4 volts. Channel, yes or no? No channel. Show of hands for no channel. That's brave. Show of hands for no or yes channel. There's 1, 2, 3, 4. The others are all unsure. Threshold voltage is the minimum voltage required to turn on MOSFET. We need to create the channel. So if it's 2 volts and you're applying 4 volts, you're exceeding the threshold voltage. So yes, channel is formed. Minus 4 points. I just messing with you. Please speak up. Yes, no worries. There's no penalty. MOSFET is on. All right, so cutoff is out of the question. The only thing remaining is to determine whether it's in active saturation mode or whether it's the linear triode region. Okay, in order to do that, we look at VGD, the gate and the drain. So if you look at VGD, what do we get? VGD is 4 minus 2.8, right? VGG is 4 volts. DS is 2.8. It's all connected, the same reference point at the bottom. And so it's 4 minus 2.8, which is 1.2. Now we check if this VGD is less than the threshold voltage. The answer is yes. So since VGD is less than the threshold voltage, the device is in the saturation region. Okay, it's in saturation region. If it's greater than the threshold voltage, then it's in the linear region. In the saturation region, because if it's less than threshold, the drain end is going to be reverse bias. Depletion region is large, channel pinches off. If it's larger than threshold voltage, then the depletion region is at its original level, it does not get pinched off. Okay, so this is the criteria you need to check. Again, remember when we apply VDS, we are reverse biasing both the drain and the source. We are reverse biasing a PNN junction, then the depletion region increases. Since the depletion region increases, the channel gets pinched off. Okay, and when that happens, it goes into saturation. All right, so then you can calculate ID. Now you can calculate ID by applying circuit analysis, right? Calculate ID from circuit analysis, or alternatively, we can also calculate it from the parameter that the equations based on the parameter we saw previously. So first, let's apply circuit analysis. First method, let's call it A. You can simply apply Ohm's law in node voltage at the output. So ID is flowing through here. We can apply Ohm's law to this resistor RD. One end of RD is VDD, the other end is VDS. Both have the same reference node. So it's an easy application, a straightforward application of Ohm's law. Does that make sense to everyone? Right? You want to find drain current, apply simple circuit analysis techniques, then we'll take the longer way. So ID is simply VDD minus VDS over RD. And so it's 10 minus 2.8 divided by 100. For ID should be what, 7.2 divided by 100. So 0.072. Right? 1, 2, 3, 72 milliamps. Yeah, 0.072 amps. Do you all have the same answer? Okay. Okay. All right. All right. Then let's use the equation we looked in the previous slide. So method B, or just a different equation to use. In the saturation region, ID, begin by K, VGS minus VTN square, or VOV. So we can do 18 times 4 minus threshold voltage 2. 18, 4 minus 2 is 2, 2 times 2 squared is 4, 4 times 18, 36, 72. Same thing, 0.072. This, of course, is an idealized case, so all the numbers match up very nicely. But in real life, that's not always possible. There's always going to be some distinction between different methods. Okay. Question? Okay. All right, let's look at the third case. Third example, VGG is given as 3 volts. VDD is given as 10 volts. Measured VDS is 1.5. Measured ID is 13.5 milliamps. And RD, drain resistor, is 630 ohms. Everything else remains the same. Okay. RD is changed, VGG is changed. Everything else is the same. Okay. Okay, so first things first, VGG or VGS is 3 volts, which is greater than the threshold voltage VTN. So it's not in cutoff. So only two options. The other two options are whether it's a linear triode region or whether it's an active saturation region. So in the active saturation region, we saw earlier, we performed this test, VGT is greater than or less than the threshold voltage. So, wait, VGT saturation. Drain voltage VDS. Okay. VGD is 3 minus 1.5. 1.5 volts, which again, when you compare it to our threshold voltage, is less than threshold voltage. So it is in, what region is it in? You all should be able to do it from here. Yeah, same thing. Active or saturation region, since it's less than threshold voltage. And we can calculate ID, again, applying VDD minus VDS RD. VDD in this case is 10 minus 0.5, 630. So ID is 8.5 over 630. It should come out to 0.0135 amps. Okay. Now this one at blank for more examples. Questions? Again, recap, similar to a BJT, you can check first of all whether the device is on or off. If drain current is equal to 0, or if the drain source voltage is exactly equal to VDD, that means the device is off, it's in cutoff region, right? Current is equal to 0, meaning the device is completely off, there is no channel. Obviously, also we can look at the gate VGS voltage. VGS voltage less than the threshold voltage. Again, there is no channel formed, device would be off. Even if not even if. So the next step after that is to check whether VGS is greater than the threshold voltage. In the other two cases, VGS is 3 volts and 4 volts, which is greater than the threshold voltage of 2 volts. So MOSFET is an overdrive, meaning device is on. It could either be in the linear or active region, or it could be the saturation region. Then you look at the drain voltage with respect to the gate. If you look at the drain voltage with respect to the gate, it's less than the threshold or greater than the threshold. Okay, and would that would indicate whether the device is pinched off, meaning it's in the saturation region, or whether the channel is still existing and the device is in the linear region. The linear region, the current will keep on increasing with increasing drain source voltage, but increasing drain source voltage means you are reverse biasing the drain, which means the depletion region is increasing at the drain. The depletion region is increasing, the channel begins to pinch off. Once the channel pinched off, it drives the transistor into saturation. Questions? Any questions? Okay. Before we close out for today, it's about 12, 13 minutes left. I just want to talk about PMOS. So P channel. P channel devices, similar to BJTs, where you have PNP transistors and NPN transistors. Construction, operation exactly the same, except everything is now reversed. Electrons are replaced with holes, holes are replaced with electrons. So the current direction, everything, and the polarity is now opposite. So same thing happens in a P-channel MOS. You have two P-type regions. So when you have two N-type regions, you have an N-channel MOS. When you have P-type regions, you have a P-channel MOS, which or PMOS. So in a PMOS, and of course, this is being exaggerated. This is P plus, and then of course we have the gate. This is the source. This is the drain. This is the body B or the bulk. Now, here we need to apply, instead of referring to VGS, so for N channel, we refer to a positive VGS. Here we refer to as VSG. VSG. Okay. And then we refer to VDS, we refer to VSD, and VDG. Okay. So now when we refer to the threshold voltage, we do not refer to a plus or minus sign, we refer simply to the magnitude of the threshold voltage. Okay. We simply refer to the magnitude of the threshold voltage because now we apply a voltage with the opposite polarity. Okay, so in an N-channel MOSFET, we're applying positive voltage. Now we need to apply a negative voltage. So VGS would be negative. And that's the only difference. Signs and everything is flipped. And so the threshold voltage, instead of exceeding, we just need to be below. that level. Because it's a p-channel MOSFET, we need to attract holes to the surface to form the channel. And if the channel is p-type, we need to attract holes. That means we need to apply negative voltage at the gate with respect to the source. Does that make sense to everyone? Right? In an N-channel MOSFET, we need to attract electrons, so we apply positive voltage at the gate. In a p-channel, we need to attract holes, and so we apply negative voltage at the gate with respect to the source. Everything else is just flipped. Are diodes unipolar or bipolar devices? How about a BJT? Is BJT a bipolar or unipolar device? It's in the name. Bipolar junction transistor, only one student knows. How about a diode? Go back to chapter 1 and chapter 2. Diode also is bipolar device because we have both holes and electrons combining for motion of current. How about FETs? Any guesses? FETs are unipolar devices because the current flows solely due to electrons or due to holes. So diodes and BJTs are bipolar devices. FETs are unipolar devices. Only one kind of charge carrier. Okay, let's see, biasing. Do you want to get into biasing the transistor? But 53 biasing MOSFETs. All right, you know what? All right, let's end class here today, and we'll pick up here on Friday. Okay. Quiz next week will be based on MOSFETs operating modes as well as biasing of the MOSFETs, which we'll do on Friday. And I'll post a homework sometime later tonight or by tomorrow morning.